It's all about RPM, in just about every racing class in existence that limits maximum displacement. The quest to turn more RPM than the next guy rules the day. In classes where power adders are prohibited, it's quite easy to understand why this is the case. Once an engine builder has squeezed every last CFM out of the cylinder head, and torque output plateaus, the only way to increase horsepower is to turn more RPM. As RPM and valve spring pressure increases, the studs on a pedestal mount rocker arm setup will flex and eventually break. Mounting the rocker arms on a shaft instead of a stud increases rigidity tremendously, and therefore shaft mount rockers are a must in high RPM race motors. That said, rigidity is just part of the equation. Shaft mount rockers also make it much easier to achieve proper valve train geometry. With a stud-mounted rocker system, the only way you can adjust the geometry is with different length push rods. On the other hand, with shaft-mounted rockers, the centerline of the pivot point of the rockers can be positioned perfectly in relation to the tip of the valve, since the rockers are mounted on a stand. All you have to do then is measure for the correct length push rods afterward. It is this combination of improved geometry and rigidity with shaft mount rockers that enable turning more RPM. Valve train stability is what everyone is after, and shaft mount rockers are a great way to accomplish this. Years ago, people put plexiglass on valve covers, and recorded the valve train movement with a high-speed camera. They were scared by how much things moved around even with stud girdles. This reinforced what racers had known all along, which is that stud-mounted rockers didn't provide enough stability in race motors. The notion that you need to step up to shaft mount rockers at a certain RPM is a bit misleading. The stress imparted on a rocker arm is a product of both spring pressure and RPM. Spring pressure is actually what tries to rip the stud out of head. Fortunately, race engine builders don't have to deal with all the design parameters that the OEMs have to. In racing, we don't need to worry about whether or not the valve covers will fit under an AC compressor. We just build a new valve cover that will fit around the cylinder head and rocker arms. At the Pro Stock and Comp Eliminator level, the increases in horsepower we're seeing today are directly related to the loft curve built into the cam. Do it right, and it's like having a variable duration camshaft. At 8,000 revolutions per minute is where the loft curve comes into play. Generally, a smooth loft curve will give an additional 0.008 inch of lobe lift by 8,000 revolutions per minute. That figure increases with RPM, so by 10,000 revolutions per minute you end up with an extra 10-15 degrees of duration. However, accomplishing this is much easier said than done. You want as much valve speed as you can get, but you have to balance it with the proper rate of valve acceleration to maintain valve train control. The rate of the springs, and the weight of the coils, retainers, and locks must all be optimized. With larger base circle cams we can now get up to 0.600 inch lobe lift. This allows us to use lower ratio rockers so the initial valve acceleration isn't as quick, which helps stabilize the valve train. Getting the valve springs to live isn't difficult if you have a limited amount of valve lift. However, cylinder head technology has improved dramatically in the last 10-15 years, so now we're picking up the valves much more than ever before. That puts much more stress on the valve springs. For a while, the focus was on the metallurgy, wire thickness, and alloy of the springs, but several years ago manufacturers realized that impurities in the spring wire were causing them to break. As a result, using clean wire in the springs is a top priority these days. Furthermore, what we've learned in the last 4 to 5 years is that you don't need enormous spring diameters anymore. Not too long ago, we used to have double and triple duty springs with 1.600 inch diameters. What happened was that the springs were getting so big and heavy that you needed higher spring rates just to control the weight of the spring. With the better, cleaner metal we have these days, engine builders are using smaller diameter springs. Smaller springs also let you use smaller retainers, which further reduces valve train mass. A great example of this is a beehive valve spring. By reducing the diameter of the top of the spring, it cuts down on mass as well. Our 99 Camaro drag car has an LS motor that turns 9,600 revolutions per minute. The exhaust valve springs are just 1.550 inches, but they have 1,000 pounds of open pressure. In recent years, a lot of progress has been made with regard to valve springs. One of the newer trends is that we are now designing springs for specific applications. In the past, we would try to find a spring that we thought would suit a specific engine combo. In a lot of cases now, we will create a clean sheet design to get the spring ideally matched to the rest of the system. The biggest advantage to the newer springs is the reduction of mass. I'll also say we have only started to scratch the surface with regard to spring design and materials. The metallurgy, spring design, and overall size of the spring all contribute to the performance of a spring. You can spend all kinds of time and money designing the best cam in the world, but unless you can get the valve to properly follow the lobe profile, all that R&D work is worthless. Any flex in the valve train means that the valves are not doing what the cam wants them to do. The goal is to have extremely stiff parts, and this is particularly true with the push rods. Up until the early 90s, engine builders thought that as long as the pushrod didn't bend, everything was okay. Now we've learned that even if a pushrod doesn't bend, it can still flex tremendously. To combat this, the trend these days is to use giant diameter pushrods. In racing classes that allow it, using a shorter deck height block is also common. This allows using shorter pushrods, which reduces both pushrod flex and mass. In fact, GM Performance Parts sells low deck height small block Chevy blocks that have an 8.325-inch tall deck opposed to a standard 9.025-inch tall deck. The Spintron is a great tool that helps simulate valve train dynamics, but it by no means has the final answer for everything. Interestingly, a loft curve that looks great on the Spintron does not necessarily correlate to good numbers on the dyno and at the track numbers. That's because a Spintron can't simulate the crankshaft pulsations that are transmitted into the cam belt and valve train. It's just another example of why there is no substitute for real-world testing. Only after dyno testing can you begin fine-tuning the loft curve. Camshafts with larger journal diameters definitely decrease how much the cam flexes, but one of the biggest advantages of larger journals is much simpler to understand. When you're sliding a cam into a block, the amount of lift you can pack into the lobes is limited by the size of the cam bores. If you make the lobes too big, the cam won't physically fit inside the block. That's where big journal cams come into play. Many aftermarket blocks are available with larger diameter cam bores. This allows installing a cam with larger, more aggressive lobes. To achieve any given amount of valve lift, you generally want the most lobe lift as possible with the lowest rocker arm ratio possible to help stabilize the valve train. The reason why NASCAR Sprint Cup teams use 2.4:1 rockers is because they have to run flat tappet cams that can't accelerate the lifters as fast as a roller lifter motor. Since they can't run as much lobe lift as they'd like to, they have to make up for it with higher ratio rockers. If you're racing in a class that allows it, using a larger journal cam with bigger lobes and a lower rocker ratio is a better way of achieving high valve lifts. With a 50mm cam, about 0.440-inch lobe lift is the limit, and with a 60mm cam you can get about 0.590-inch lobe lift. Reducing mass, or weight, is more critical on the valve side of the rocker arm than on the pushrod side. From the rocker arm to the lifter, increasing stiffness will be more advantageous than reducing mass every time. The goal here isn't to go after the lightest weight parts when considering a lifter or pushrod. The top priority is increasing stiffness and reducing flex. With regards to pushrods, I would recommend going with the largest diameter, thickest wall pushrods you can fit in an engine. On the valve side of the rocker arm, weight is much more important. Here, It's critical to get the locks, retainers, and springs as light as possible to reduce inertia. Reducing mass.
Thank you for watching. Don't forget to subscribe or like.